In this, another exciting video in our never-ending lecture series on chemical equilibrium, I will continue teaching you about chemical equilibrium. In our previous lecture, I taught you guys about Kc, the equilibrium constant, dynamic equilibrium, static equilibrium, and how to derive Kp, the equilibrium constant with respect to pressure, from Kc, the equilibrium constant with respect to concentration. I'll, of course, link to all that here. We're going to continue talking about this by saying that you can also calculate the equilibrium constant for a reaction if you know the equilibrium constants for other smaller reactions that, if you add those up together, give you an overall grand reaction. Hopefully that makes sense. So once again, if you've got multiple small reactions that, if you add them up, give you a final overall reaction, algebraically speaking, and you have the K numbers, or the equilibrium constants for each of those, you can actually manipulate them algebraically to give you the overall equilibrium constant for the overall reaction. This is reminiscent to what we did with thermodynamic data from Hess's law, hailing back to Chapter 5 lecture, to which I'll link right here. So doing this simply involves moving individual equations around so that they add up to give the target equation of interest. Here are some important details you should know, however. First, Kc for a reaction written in one direction is the reciprocal of Kc for the same reaction written in the opposite direction. In other words, Kc in one direction is equal to 1 over Kc of the reverse direction. Got it? Next, you can multiply all of the reactants and products in a reaction by any number you want, as long as you do it by the same number across the board. When you do that, however, you have to raise the reaction's equilibrium constant Kc to the power corresponding to the number that you multiplied with. In other words, I multiply through everything in a reaction, its Kc gets raised to that power, or exponent. Next, when you add reactions together to give a new reaction, you have to multiply the individual equilibrium constants for each of those sub-reactions together to get the overall equilibrium constant for the overall reaction. Hopefully conceptually that makes sense. Let's take a look at an example. Given these reactions, what is the value of Kc for the following reaction? I'm not going to do this for you, but you're welcome to pause the video and attempt it on your own. Then, if you wish, you can click the link here to a separate video in which I work it out on the whiteboard. And now to this question. The following equilibria were obtained at 823 Kelvin. Based on these equilibria, what's the equilibrium constant for the following reaction at 823 Kelvin? Similarly, I won't work this out here. You're welcome to pause the video and attempt it on your own first, and then if you wish, you can click the link here to a separate video in which I'll work it out on the board. Now I'm going to teach you about heterogeneous equilibrium. Now, equilibrium reactions in which some of the substances are in one phase, solid, liquid, gas, or aqueous, while others are in other physical phases, solid, liquid, gas, or aqueous, are called heterogeneous equilibria. For reasons that I won't bother explaining here, solids and liquids do not appear in the Kc, or equilibrium constant, of equilibrium reactions. For instance, the Kc for this reaction happens to be this. Notice that this lead chloride reactant shown here at the left side of the equation is omitted. The reason is because it is a solid. Similarly, liquids are also omitted from equilibrium constant expressions. With that solidly locked in your mind, let's take a look at a problem. Which of the following is the correct equilibrium constant expression Kc for the following reaction? Keeping in mind what I just barely taught you, I'll let you attempt to do this on your own. And next, which of the following expressions is the correct equilibrium constant expression for the reaction below? Similarly, I won't do it, but we'll let you attempt it on your own. That takes us to the end of this presentation. Please stay tuned to the next one, in which I'll continue teaching you more about chemical equilibrium. Until next time, have an enjoyable rest of your day.